We're going to talk about section 5.2, graphing logarithms. Before we get to that, let's recognize that exponentials and logarithms are inverse functions. They're inverses of each other. So first, before we get to the graphing part, algebraically, that means that f of f inverse of x is equal to x, and f inverse of f of x is equal to x. Let's see, that would mean that if f of x is 2 to the x, then its inverse is going to be logarithm base 2 of x. If we knew that, say, f of 4 is going to be 2 to the 4th would be 16, then f inverse of 16 would be a logarithm base 2 of 16 would have to be 4, because f of f inverse of 4, they would have to undo each other. Similarly, we could say that the logarithm base 2 of 2 to the 4th, here now you can see this f inverse of f happening right there. They're going to essentially cancel each other and leave us with 4. Likewise, if we took f inverse of 8, that would be the logarithm base 2 of 8. And I don't know if you can recognize it. 2 to what power is 8 is going to be 3. We could also say that f of 3 is going to be 2 to the 3rd is 8. So we could say that f inverse of f of 8 is going to be the logarithm base 2 of 2 to the 3rd. And here again, you can see the f inverse of f coming into play there. Or we could say f of f inverse of 8 would be 2 raised to the logarithm base 2 of 8. And we could see that these would cancel each other and give us the 8. Okay? Let's look at a couple other inverse functions. H is e to the x, and h inverse is going to be natural log of x. That's a logarithm base e of x. So, for example, if we said what is h of 3, that would be e to the 3rd. So if we turned right back around and took that e to the 3rd into the inverse, then we know that because an exponential base Euler's number and a logarithm base Euler's number are inverses, we have to get back to the 3. Similarly, if we said what is h inverse of the square root of e, that would be the natural log of the square root of e. Now remember, we can write square root as e to the 1/2, and now you can see, again, a logarithm base Euler's number and an exponential base Euler's number are going to cancel. That's going to have to be 1/2. Okay, let's look at what base is 10. So these are also commonly used. So we know, for example, that g of 2 is 10 to the 2nd, which is 100. So if we turn around and put that into the inverse, that would be the log of 100, which again we could think of as a log of 10 squared, where we can see a logarithm base 10 and an exponential base 10 are inverses. They're going to cancel each other and give us just the 2. Now this would be true even if we did something that wasn't obvious. If we took g inverse of, say, 7, that would be the log of 7. I don't know what that is off the top of my head, but if we turn around and then take g of g inverse of 7, that would be 10 raised to the logarithm of 7. That's a logarithm base 10 of 7. But we know that the exponential base 10 and the logarithm base 10 are inverses, and so you would get just 7. Okay, I'm going to go to a new panel here. So here, let's talk about the geometric interpretation of exponentials and logarithms being inverses of each other. So we have here in the yellow 2 to the x, and in the green logarithm base 2 of x. Let's graph the y equals 2 to the x. I think that's a little easier. When we plug in 0 for x, we're going to get 2 to the 0 is 1. So I'm going to label that point 0, 1. When we plug in 1 for x, we're going to get 2 to the first, which is 2, and so that'll give us the point 1, 2. If we plug in negative 1 for x, then we're going to get 2 to the negative 1, which is going to be 1 half. So that's going to be the point negative 1, comma 1 half, and it's going to do something like this. There's our exponential growth function. We can see that we have a horizontal asymptote at y equals 0. Now, because a logarithm is an inverse of the exponential, we can plot points by just switching the x and y coordinates of the ones we just found for 2 to the x. So the point 0, 1 will become the point for the logarithm 1, 0. The point that was 1, 2 will become the point 2, 1. Trying to put this where it won't be in the way. And the point negative 1, 1 half will be 1 half negative 1. Now we also see that this thing is going to rise from left to right. So it's also increasing. The 2 to the x had a horizontal asymptote of y equals 0, and the logarithm will have a vertical asymptote of x equals 0. And hopefully we can see these graphs are reflections of each other in the line y equals x. If you fold on that red line, the green and the blue and the yellow functions should land on top of each other. So let's compare now these four functions: 10 to the x, e to the x, log of x, and natural log of x. So first the 10 to the x. So we know that at 0 it's going to go through 1, and at x equals 1 it's going to be way up at 10. I'm going to call that right up there. And at negative 1 it's going to be a 1/10, which is going to be really small. So it's going to really hug that x-axis pretty quick, and it's going to rise very steeply once it crosses our y-axis. Now the blue, e to the x, it's also going to share that 0.01 because e to the 0 is still 1. When we plug in 1, it's only going to be e to the first, which is e, which is about 2.7. So it's going to be much smaller than that 10 was for 10 to the x. Likewise, when we cross over and plug in negative 1, we're going to get 1 over 2.7, which is roughly 1/3, and that's going to be bigger than the 1/10 that we had from that 10 to the x, 10 to the negative 1. So we're going to get still exponential growth, but it's going to be more leisurely. It's going to rise slower, and it's going to hug the x-axis slower as well. Now let's look at these logarithms. So I'm going to get my green pen up here. So for log 10 of x, when x is 1, we're going to get 0. And when x is 10, we're going to get 1. So it's going to be way out here. When x is 1/10, we're going to be at negative 1. So we're going to be way over here. So just as we saw that yellow graph is going to really hug the x-axis, this is going to hug the y-axis and bend over quickly there too. So I like to think of those as trying to look like right angles as much as they can. And likewise, the natural log is going to share the point at 1, 0, but it's going to be at 1 by the time we're at about 3. So it's going to be something like that. And at 1 over e, it's going to be negative 1, which is going to be more over here. So it's going to look something like that. Okay, let's add another dimension to this. Let's see if we can graph some of these and also talk about their domain and range and their x-intercept and their asymptote. So when I ask you to graph a logarithm on a test question, I don't want you to plot a whole bunch of points. I'm hoping that you know that the basic logarithm curve is going to look this is our parent function, is going to look something like this. The x minus 2 is going to translate everything 2 to the right. So that means we're going to be at, I'm going to stay with the yellow, I think. So if we go 2 more to the right, that's going to make the x-intercept be 3, 0. It's going to move that vertical asymptote from x equals 0 to x equals 2. So that's going to be our x-intercept, and it's going to have that same logarithm shape. So those are the three things that I'm looking for when you graph these, is where does that point that was the x-intercept, where does it end up, what's the asymptote, and what's the basic shape. Now you can see for this that our domain is going to be x strictly greater than 2, and that our range is going to be all real numbers. Let's look at the next one. We have now the natural log of x plus 2. I'm going to come over here a little bit. And again, we have our basic parent function is going to be, this is our standard logarithm graph, and the natural log doesn't really look a whole lot different unless we're going to plot a whole bunch of points. Now the translation is going to be 3 to the left, so this important point, the x-intercept, is going to go 1, 2, 3, so it's going to be at negative 2, 0. That asymptote that was at the y-axis is going to get moved 3 to the left as well, and make sure you give that as an equation, not just as a number. That's going to be x equals negative 3, and its shape is going to be that typical logarithm shape where it's going to rise from left to right and be concave down. Its domain is going to be x strictly greater than negative 3, and its range is also all real numbers. On to our third one. This is now a logarithm base 10. Again, our parent function is this basic logarithm. This 3 is going to, let's first talk about maybe the x minus 1. It's going to translate everything to the right one. So this point is going to be where it crosses the x-axis. The asymptote also is going to get moved to be x equals 1. Now it's going to be kind of hard to tell exactly what happens, but this is a vertical stretch, which means each of these y values is going to be 3 times as tall. So it's going to kind of bend it more that way, but really hard to see much difference in a logarithm graph what that exactly is doing. Domain here, again, going to be x strictly greater than 1, and range also all real numbers. So let's do some exponentials. We'll add some translations now. So here's our xy axis. Our parent function for exponential growth is going to look something like that. And plus 3 is going to translate everything up 3. So in particular, our y-intercept is going to be at 0, 3. And it's going to move our asymptote from the x-axis to, that's going to be 0, 4, because we have to move it up 3 from the 0, 1 that it was. So it's 0, 4. The asymptote is going to get moved from the x-axis up 3, so it's going to be y equals 3, and it's going to rise from left to right. So those are the three things, again, I'm looking for an exponential as well. a y-intercept, an asymptote, and the basic shape. Our domain and range are going to be switched for an exponential compared to a logarithm. So its domain is all real numbers, and its range is going to be y strictly greater than 3. So our next one, we see because the base, 1/7, is less than 1, we're going to have our parent function is going to be a decay function. The -2 is going to translate everything down 2, so that asymptote in particular is going to go from the x-axis to y equals -2. That y-intercept that was at 0, 1 is going to go down 2, so it's now going to be at 0, -1, and its shape is still going to be that decay curve shape, falling from left to right, concave up. So the domain is still going to be all real numbers. The range here, because of our translation, is going to be y is greater than, strictly greater than, -2. Okay, let's do one more here. So we've got our xy axis, and this is the 2 to the x is exponential growth. So that's our parent function. The 3 is going to multiply everything by 3, all the y values. So in particular, that y-intercept is going to go from 0, 1 to 0, 3. All of the heights here are going to get multiplied by 3. So it's not going to be quite exactly the same shape as it was, but it has not changed the asymptote yet. The -1 is a translation, so everything's going to get moved down 1, including that asymptote. So that's going to make the asymptote be y equals -1. That y-intercept that got stretched to 0, 3 is now going to get moved down 1 because of the translation. So it's going to end up being at 0, 2, and our shape is going to be that stretched exponential growth curve. All right, very good.